So far, we dealt with artificial neural network, which is very suitable for the tabular data. Uh, and we have also dealt with CNN, which are suitable for image data or video data. And most of the time, that data is in the form of a grid structure. So these two are very excellent tools for that particular application. So, especially CNN, they are much used in computer vision related tasks. The CNNs are highly successful, and they are very effective in that domain. But there are certain problems with ANN or CNN. The first problem that is this CNN or ANN, they ignore the sequence of input, the order of the input. So when you have such features x1, x1, x2, x3, and they are fed to another hidden layers, let us say, and these are one structure, one units and one weights and another weights here. So whether you take this in the order x1, x2, x3, or x2, x1, x3, or whatever order you take, it doesn't matter because we always fed the data, all the data once. We feed all the data at once. So as a result, uh, we cannot capture the sequence information. In case of images, there is no part of sequence, but when we talk about NLP applications, the semantic analysis or identifying the parts of speech, we need sequence. For example, if I say, I love teaching, there's a sequence. First, the object, then subject, then a verb. That is a sequence. You cannot write teaching love I. This is utterly wrong. So, especially in the NLP related tasks, we need sequence information to be captured. We cannot completely ignore the sequence information. So we have to consider the sequence information without fail. That is very important, and it will have many applications in real world. The second problem with the second problem with ANN and CNN is they cannot handle variable length inputs. Variable length. We know that whether it is ANN or CNN, we have always fixed size of input. This is our input layer. For example, if you see the input layer, it is only 3 units. So for all the training, it will be fixed. But in real-time scenario, whenever we talk about NLP, now suppose you are doing a problem of sentiment analysis. What is sentiment analysis? Sentiment analysis is a textual analysis where you will review all the reviews of a product or a movie, then you will classify it as a positive review or a negative review. So, when we talk about review, one review may have 10 words, that means 10 inputs. Another review may have 100 words, and another review may have only one word. So, ENN and CNN, they are not structured or designed to handle variable length inputs. Variable length inputs. So these two are the major problems with ANN and CNN. So to overcome these two problems, what are these two problems? First problem, considering they don't consider the information present in the sequence. And second problem, they cannot handle the variable length inputs. To address these two problems, we have RNN, recurrent neural networks. Recurrent neural networks. We'll see why they are called recurrent neural networks, why that name has come as we discuss the structure of that. So, firstly, RNN, they will consider, they will not ignore the sequence information. So, RNNs are suitable for sequential data. What is sequential data? One step of the data depends on the previous steps. Suppose t, at time t, the data depends on time t minus 1, time t minus 2, time t minus 3, so on. It depends on previous steps. So in NLP, we have this text data is considered as sequential data, then speech audio data is also considered as sequential data, DNA sequence that depends on the previous sequence. Similarly, stock prediction, stock market share price prediction. So to predict a share price, you need to analyze all the previous stocks also, share prices also. So these are sequential data. So now what is our summary? CNN grid structure data used in computer vision, RNN sequential data used in NLP related tasks. That's why this chapter of fourth unit, we call it as sequence modeling. We call this as sequence modeling. Now let us see how this RNN works and what is the architecture of RNN. To understand the structure of RNN, let us consider a simple problem of sentiment analysis. Let us take a most simple and very primitive sentiment analysis problem. Let us say we have 3 reviews. I will call them as X1, X2, and X3. 3 reviews. And let us say I am reviewing a phone. So the first review says phone is good. A simple review. And what is this review? Is it positive review or negative review? It is a positive review. So it is 1. So this is review. This is sentiment. then phone is bad. So this is a negative review, 0. Then another review, maybe phone is not good. Obviously, this is also a negative review. So we have 3 reviews and 3 outcomes. Now the question is, how do we send this data into RNN or a neural network? So one first method we should understand is this text data is vectorized. So there are many methods of vectorization like word-vec and other methods. And in this example, we'll consider one simplest method known as one-hot encoding. One-hot encoding. So now what we do is in our reviews, that means all the words that are present in our vocabulary in this problem. How many words are there? So phone is a word, then is a word, good is a word. Then this coming to the second review, good already is covered already, bad, then, so totally 5 words are there. 5 words are there. In one-hot encoding, what we do is we give 5-digit code to each word. So let us say phone is represented by 1 followed by 4 zeros, and this is represented as 0, 1, 3 zeros. This is represented as 0, 0, 1, 0, 0. This is represented as 0, 0, 0, 1, 0. And this is represented as 0, 0, 0, 1. So these are the codes that, and this data is supplied to RNN based on 2 aspects. One is time steps, how many maximum number of time steps. And secondly, it is number of features, how many number of features are there. So time steps means, now when t is equal to 0, I will send this first word. I will call it as x11. And when time is equal to 2, or time is equal to 1, I will send x11. When time is equal to 2, I will send x12. And when time is equal to 3, I will send x13. Then time is equal to 4, I will send x21. Then 5, x22, x23. That means this is 3 time steps. 3 time steps. And here we have 3 time steps. And here we have 3, 1, 1 time, 3, 2, 3, 3, and 3, 4. So here we have 4 time steps. So what we tell here is, in this example, number of time steps are 4, and features at each word is represented by, irrespective of its length, each word is represented as the number of time steps, that means number of features. So 5 features are there for each word. So this, let us say I'm doing when t is equal to 1. My input is phone, first word. And what is the code for that? 1, 0, 0, 0. So if you can draw a diagram, so this is 1, 1, 0, 0. So this is 1, 0, 0, 0, 0, 4 zeros. So this is my input layer. Let us say I'm assuming that I'm dealing it with 3 hidden layers. So each one will be fully connected to all the three layers. So we can draw all the connections. So these are the features, input features. Generally, we indicated them by X. So at time t is equal to 0, we can also represent it like a block diagram. When time is equal to 1, I have this features. I'm sending it, let me, I'm sending x1, 1 when time is equal to 1 to the layer, hidden layer. And from the hidden layer, we can get output. This is time 1. Next, now what we have to understand is this is our input is 1 cross 5, the size. That means 1 cross 5 is the matrix size of the input. Now this is fed to 3 inputs. So how many weights we will get? One each input is assigned with 3 weights. So totally 5. 5 into 3, 15 weights. So our matrix of weights is 5 cross 3. So totally 15 weights we have. And that weight matrix, we call it as U. What is U here? Weights of input, weights for input, weights for input. Then, once we do that, I will get my hidden layer, H. You can call it as H11, let us say. And once H1 is there, generally in any neural network, what we do is we calculate another set of weights. We'll have how many weights we'll have? We have 3 and they are going to only 1. So the weights here are 3 cross 1 weight. 3 weights are there. And of course, bias also would be there. Here we have 3 biases and here we have 1 bias. So here V, what is V? V is weights for from hidden to output. Weights from hidden to output, right? So once we do this, we'll get the output, let us say O1. From the O1, you can calculate the Y. So now, in the time 2, you will do the same thing. But the speciality of RNN is once you calculate H1, that H1 is sent then the next time step when t is equal to 2, you will send x12 with the same weights u, and you will be producing h12, and with weights v you will be producing O2. But the major aspect of RNN is while it produces h12, it takes feedback from h11 with a weight w. So what is w? W is weight from hidden to hidden, hidden to hidden. So major prime aspect of RNN is that it has memory. That means the present output depends on the previous output. H11, here we don't have any previous. So what we do is we take some random H00 and the same weights. So totally we have three weights here. That means this output, whatever it is, it will give feedback to this, the same again. And the same will give output to in feedback to this. The same will give feedback to this. So there's only three are there, and three are giving, each one is giving to three. So it is 3 cross 3. So what is the dimensions here? U, input weights, 5 cross 1 or 1, 5 cross 1. Then V, output weights, 3 cross 1. W, hidden 3 cross 3. So what is that we have to understand here? You have at time t is equal to 0, you are sending x11 with a weight u, and you will get, let us say, O1 with a weight v. So here, if you write the mathematical equation, if the activation function is tan h, if that is the case, so generally you can write O1 is tan h of the weight vector u into x11 or x11 u, or let us write it the features first, then weights, or whatever it may be, w1 x1. Okay, u x11 plus the bias b. This is a general, but in RNN, what happening? We have a feedback. Okay, we'll come to t is equal to 1. T is equal to 1. T is equal to 1. This is 2. Let us not consider t is equal to 0. So here we have x12, and again we have set of weights u. Again we have set of weights v. Then O2. So then from the O1, we can calculate Y1 cap as, for example, you have sigmoid function at that function. Then V into O1 plus that bias. Now at t is equal to 1, this one. At t is equal to 2, O2 is equal to tan h u, the weight vector, into x12 plus a particular bias. But what is happening there? The O1, the output, is given as input to this vector. So we are also having O1, or in the other earlier we have said H1 into a particular weight. Here also, to maintain the consistency, we write H0, some random, into W. So this is RNN. So we say that RNN uses some memory to represent or to remember, rather than represent, to remember the previous in outputs, which is not there in, this feature is not there in other CNNs. So to generalize, for example, you have here Don't bother about the notation, whether it is H1 or ON, that is not a big deal. You understand that at a particular time t, the hidden unit or the output unit OT is calculated as the activation function into of the input weights U and the present X plus the bias plus weights of the hidden units or feedback weights W into OT minus 1. So OT depends on OT minus 1. So if this is XT, which is going with weights U, and here we have OT minus 1 coming with the weight vector W, and this will be calculating the OT, and this OT again with the weight to the V, it is used to calculate Y. So from OT, we calculate Y cap as another activation function, let us say F dash, into the weight vector V into OT plus that particular bias. So this is the structure and working of the, what we say, structure and working of RNN. So in the next classes, we are going to see the advantages and not advantages. What we are going to see? We are going to see the forward propagation and also the backward propagation. Okay, thank you.